Hello and welcome. I love you all. You all are doing wonderfully well. Comments, likes, many of you chatted me on WhatsApp. You are doing wonderfully well. And because you requested that this topic be taught, I have to do it now. I have to leave many other things I was supposed to do or be doing now to do this. Alright, so let's look at this. A metal of mass 0.5 kilogram mass is heated to 100 degrees Celsius and then transferred to a well-lagged calorimeter of heat capacity 80 joules per Kelvin containing water of heat capacity 420 joules per Kelvin at temperature of 15 degrees Celsius. If the final steady temperature of the mixture is 25 degrees Celsius, find the specific heat capacity of the metal. What is the answer? So many of you can solve this. So now, if you can solve it, no, some of you will check. This is in the past questions. I can solve it. Some of you will check and find out how it is solved. But there are some things I will tell you now. Now look, I am the driver. You are like a passenger. As I'm moving, if you jump out at your own risk, so move with us until we get to the end. The whole of the video you are going to have your watch all till the end. There are some things I'm going to show you. You are going to have some assignments. So I'm going to break this down with other similar information that you need to get. Now look at this. Well-lagged calorimeter. I have a calorimeter. Let me show you a calorimeter. Okay, this is a calorimeter. Right? Now, this is what we call stirrer. This stirrer is for uniform distribution of heat. If you have a bucket of water, if you are with a bucket of water at normal temperature, if you pour hot water at the middle of the water and dip your hand there, that center or middle will be very hot, but the sides will be cold. Mind you, we don't test temperature with our finger because you use the test, you determine temperature using what? Thermometer. But when you do this perform this simple experiment, see that the sides are not of the same temperature. Why? Because the water you poured at the center has not really distributed. So it spreads with time. So we use this stirrer to ensure uniform distribution of heat within this calorimeter. We use this to determine heat, quantity of heat. I hope you can understand that. So now, in this, I know the reason because sometimes students are asked some questions under this. This is that copper here. See the lagged calorimeter. This thing that is here is just like a foam or a cotton wool rather. So you look at it. Now look at it. Heat can be lost by conduction, convection, or radiation. Assignment. This lag here prevents heat loss by what? Put your answer in our comment section. This prevents heat loss by what? The purpose of putting this is to prevent heat loss. So take note of that. It can come as theory, it can come as objectives. Now let's solve this question. In something like this, what you should know is this. A metal, you have to determine the solid that lost metal or the part that lost heat, and the one that what? Gained heat. Now let me ask you, look at this question. Metal of mass, a metal of mass 0.5 kg is heated to 100 degrees Celsius. Now, and is transferred to the water and calorimeter 15 degrees Celsius, 25 degrees Celsius. This metal is at 100. So when you transfer it into the calorimeter as I've shown you, it will lose heat. It will lose heat to the water and the calorimeter. Just like taking a hot object, putting it inside another object that is not hot, or liquid that is not hot. That one that is hot will supply heat to the one that is cold. So that is what you should always look at. Now here, in this scenario, this metal has lost heat. The calorimeter and water gained heat. So now, for heat, most of the time, the formula is mass, capacity, change in temperature. Mass, specific heat capacity, then times change in temperature. This is for the metal. Then, heat loss or lost heat, just call it heat loss. That is the language. Heat lost equal to heat. Let me put it like that, the same thing. Heat gained, still the same thing. So now this is the formula. This is the formula. Mass, capacity, change in temperature equal to, you know, what are the things that gain heat? The calorimeter will gain heat. The calorimeter will gain heat. This thing, this calorimeter here will gain heat as a solid. Then the water inside it will also gain heat. So these two will gain heat from that metal. So now we have to add it, mass of calorimeter, heat capacity of calorimeter, and the change in temperature of that calorimeter, plus mass of the water, heat capacity, specific heat capacity of water, times change in temperature of water. This is it. So we can call this one metal, change in temperature of metal. Well, I wish you have enough time. I will have, taken time to teach you this, right? There are two methods of determining what? Specific heat capacity. We have what? Electrical method and method of mixtures. This one is called method of mixtures. That's what we are doing now. Now let's look at this now. So we are going to fix these values in this. We are going to fix these values in this. Now, mass of metal is 0.5. So write it 0.5. Specific heat capacity of metal. This is what we are looking for. So times C. Change in temperature of metal. Now the metal was at 100 degrees Celsius and now steady final temperature 25 degrees Celsius. Look at it, from 100 to 25. So you now have what? So there is change in heat here. Change in heat is what? 100 minus 25 for the metal, right? All right, let's continue it now. Okay, so this is equal to, look at this now. The main reason I gave you this question is this. It brings confusion. Confusion. We are going to avoid this now. Look at this. Let me bring it here. Let me show them. Let me show it here. Heat capacity is equal to mass times specific heat capacity. Look at it. Now look at this thing. What this thing means is that this one is not the same as this. What we have done here is not the same as what we are going to do there. Watch. Look at this unit. Heat capacity is given in joules per Kelvin, but specific heat capacity is given in joules per kilogram per Kelvin. This one involves mass. Joules per kilogram per Kelvin. So now look at this unit. So now what it means is that the value of this mass and specific heat capacity have already been given in this. So the only thing that we need is to use this. So the whole of this thing will now change to possibly C that times change in temperature of calorimeter plus heat capacity times change in temperature of water. This is it. So now it is very easy. Be cognizant of that. Take note of that. Oh. Let that not confuse you. Always check the units before you now start looking for mass. You say, hey, they did not give us mass here. It's already in this one, right? So now we have this 80 joules per Kelvin for the calorimeter. Then this one is for what? For water, heat capacity of water. So now we are continuing. We can continue. It's not a very difficult thing. Watch. The heat capacity is the quantity of heat required to raise the temperature of the whole mass. That is heat capacity. Heat capacity. Sometimes it is given symbol Q. Heat capacity. Temperature of the whole mass of the object. But specific talks about what temperature required to raise a unit mass. This is what you should know about. Specific. The specific means the temperature required to reach a unit mass. But quantity of it means temperature required to raise the whole mass. Take note of that. So let's continue. This is very simple. Alright. So this mass and capacity, which is quantity of it, is already given. So it's what? 80 times change in heat is what? Change in heat is what? Look at it. It is from at 15 degrees Celsius and 25 It was at 15. Then when it gained heat, it increased to 25, which means it gained 10 degrees Celsius from the metal. Now, so bracket 25 minus 15. You can see what I did here. This one will lose it. This one will lose it. 100 minus 25. This one gained it. 25 minus 15. 25 final temperature minus the initial temperature plus mass of water and the heat capacity of water, specific heat capacity of water. Mass of water and specific heat capacity of water are already given, making it quantity of heat, which is what? 420. So write 420 times change in temperature, the same thing, because the two of them are of the same temperature, right? So we now have 0.5, 100 times minus 25 will give us what? 0.5 times C times 75 equal to 80 times 25 minus 15, 10 plus 25 minus 15, 10. Well, it's 420 times what? 10. Alright? We'll do it like this. Because of this plus, we put it in brackets. So 0.5, which is like 1 over 2. 1 over 2 times 75. That is 75 divided by times 0.5. That is 75 over 2. Will give us 37.5 times C. That is 37.5 C equal to 80 times 10 is 800 plus 420 times 10 is 4,200. So this and this will give us 500. So we have 37.5 C equal to 5,000. 5,000. So the specific heat capacity finally is 5,000 over 37.5. When you divide this, it can give us 133.3. So this is the answer. This is the answer. When you divide this, it will give you 133 joules per kilogram per Kelvin. So this is the answer for this very one. Now, most of the time, you don't have questions like this. They always give you simple questions involving electricity. That is the electrical method, IVT, I square R, and all those things. So let's look at one or two of such questions now. Alright, this is a very nice question. It's a very nice one. Electricity. In the other question I solved now, we had the energy supplied by the metal. The metal supplied the heat. But this time, the heat is coming from electrical energy. Electrical energy, right? So what we are going to do now is to solve the question. Look at this. Look. This is a very nice question. Now, you know, normally, electrical energy, power is IV. Then electrical energy is IVT. It's not like the one of mechanical that's mgh over time. Be careful of this. So electrical energy is IVT, not mgh over time. It's IVT. Now let's look at it. So from this question, it is used to boil just water. Boil water, boiling of water. It's a very simple question. Now, in case you are not given potential difference V, you know by Ohm's law, V is equal to IR. So you can substitute V here. By now, with I times IR, that is what? I square R. Then here it will become I square RT. Like this. So in case you are not given potential difference, if you are not given current I, you can still substitute it. Current is V over R. You now substitute it. That is V square over R. Any one you are given, you can substitute it. Don't say Mr. Primus did not tell us that. Oh. Just be careful about that. Alright, thank you very much. Now let's look at the question. So for this energy supply, which is IVT equal to mass, specific heat capacity, change in temperature, water. Alright, what is the current there? Okay, let's just find it directly. It says if the mass of the water is 2.5 kg, determine the time taken to boil the water. So 2.0 amperes, 2.240 volts, 52 degrees Celsius, 100 degrees Celsius, and all these. So let's get our T time. We now have Mass, specific heat capacity, change in temperature over what? Over current times potential difference. So the time taken in seconds is equal to, what is the mass? 2.5. So M 2.5 times specific heat capacity. C is what? Look at it. Specific heat capacity of water is given to us. We see it here. In another one, we were given heat capacity 420 joules per Kelvin. Now specific heat capacity, this one is 4,200 specific per unit temperature. So now I have 4.2 times 10 raised to the power what? 3. Then times the change in temperature. Look at it. 152 to 100. Change in temperature is final minus initial. That is 100 minus 52. 100 minus 52 will give you what? 48. I'm solving it directly like this. All divided by what? The current. What is the current? 2.02 times. What is the potential difference? 240. Now, when I did UTME during our time, we were not required to use calculator. So something like this, you don't need to look for calculator. Standard form, indices. Standard form, then indices, finish it. And that's why you have been given options like this to see how good you can still approach it without calculator. So permit me to do something like this. 2.5, if you remove this point, it means what? Times 10. 4.0, to remove this point, it means what? 10. So it becomes 42 and 25. That's all. 10. To remove this point because it's 1. 10. If there are two numbers after, like let me say 253, I will write for this one 100. But it's just one number. So that's how I only have 10. I hope you can understand that. So take note of this. So we can now cut everything. Alright. So what goes? What goes? What goes? Alright. 5 can go. 5 in 25 is what? 5. 5 in 10, 2. Now these 2 can go. 2 here, 1. 2 in 42, 21. Alright. What goes again? 2 can go. 2 here, 1. 2 in 48, 24. Now this 24 can cancel this 240. 240 to give us 10 here. So we have 5 times 21 times 10 raised to the power 3, 10 times 10. So let's multiply it. 5 times 21, 5 times 1, 5. 5 times 2, 10 times 10 raised to the power 3 over 10 times 10, 100. 100 is 10 raised to the power 2. 100 is 10 raised to the power 2. So now bring this thing up here. So bringing 2, 10 raised to the power 2 up here becomes 3 minus 2. So we have 105 times 10 raised to the power 3 minus 2. 3 minus 2 is 1. So 105 times 10 raised to the power 1. Look at the options. None of them has this. So it means that we have to, bring it as it should be. So we start from here. 1 decimal place. Right? Oh yeah. 1, 2 points. So 2, if you count it like this, 1, we have plus 1, then I move it like this. Plus 1, that is 1 plus 1 plus 1, 3. So 1.05 times 10 raised to the power what? 3. Alright. See the answer here. It's a very nice question. I like this. Okay, let's look at another one that has latent heat. Latent heat. That's good. Okay, look at this question. Latent heat. Latent means hidden. Calculate the mass of ice that would melt when 2 kilograms of copper is quickly transferred from boiling water to a block of ice without heat loss. Ice, boiling water. It's only one thing that is given here. How come? Look at all these other ones. Specific heat capacity of copper. Latent heat of fusion of ice. Now, formula. For anything that involves latent heat, right? This copper is one that will supply heat to this ice. Ice, what is temperature of ice? 0 degrees Celsius. Temperature of boiling water, 100. So the temperature of this copper is 100 because it is transferred. So we have mass capacity change in temperature equal to mass times latent heat. This is the formula for latent heat. Anytime you see ice or steam, ice and steam, they involve latent heat. So I want to give you an assignment. Differentiate between latent heat of fusion and latent heat of vaporization. Differentiate between latent heat of fusion and latent heat of vaporization. Put your answer in our comment section. Thank you very much. Let's continue. So we do have mass. Yes. We have specific heat capacity of copper. Yes. Change in temperature of copper. Boiling 100 to 0. So we have mass, which is 2 times specific heat capacity of copper, 400 times change in temperature. It was, this copper was put in boiling water and removed. So boiling water, the temperature of boiling water is 100. So 100 minus 0. Alright, 100 minus 0 equal to the mass. What did they say? Calculate the mass of ice. So this is what we are looking for. Mass times latent heat. What is latent heat? 3.3. 3.3 times 10 raised to the power 5. So this mass is now 2 times 400 times 100 minus 0 is still 100 over 3.3 times 10 raised to the power 5. Look at the options, kg, in this fraction. So let's look at how to get it. Right? So now let's do it like we did it before. When you move this from right to left is minus. Right to left is minus. So we have 2 times 400 times 100 over 33 times minus 1. 5 minus 1 is 4. 10 raised to the power 4. This 10 raised to the power 4, this one means, let me put it 0, 0, 0, 0. Now let me say, we can even spread this thing in form. Let's spread it. 2 times 400 times 100. We can spread it or you do it the other way. I will do it in 2 ways now. All over 33 times 10 raised to the power 4 is 1, 1, 2, 3, 4. 0 cancel 0. That is 10 raised to the power 4. 0 cancel 0. 0 cancel 0. 0 cancel 0. 2 times 4. 8 over 33. Or I will use the other form. 2 times 4. 8 times 1, 2, 3, 4. 10 raised to the power 4 over 33 times 10 raised to the power 4. Then this can cancel this. 8 over 30. Any of the two. So the answer is still 8 over 33 kg. See it here. 8 over 33 kg. So thank you very much on this. Now let's look at another topic as many of you requested. So I decided to touch some of the topics. Mr. Primus, teach this. Mr. Primus, teach that. Let me do one of them now. Okay, look at this question. On half-life. Half-life. The time it will take a certain radioactive material with half-life of 50 days, which means after 50 days, it will decay into half. Maybe if the mass is 100 grams, after 50 days, it will decay and turn to what? 50 grams. After another 50 days, it will decay and turn to what? 25 grams. This is how it continue decaying. First half, second half, third half. Hope you can get that. So that is how it goes. Half-life. So after 50 days, this material will be decaying. Now, to reduce to 1/3 of its original number, 1 over 32 rather, of its original number. When you are giving something like this, let's solve it up here like this. How many days will it take you to get 1 over 32 of its original number? 50 days. Now, when you are giving a question like this, the first thing, under normal circumstance, this is the first half. So the second half is 1 over 2 raised to the power 2. 2 half-lives. 3 half-lives. 4 half-lives. 5 half-lives. So this one is 1 over 2. Then this one is 1 over 2 raised to the power 2, 4. 1 over 8, 1 over 16, 1 over 32. So 1 over 32 is 5 half-lives. 5 half-lives. 1, 2, 3, 4, 5 half-lives. Can you see it now? So this is how we always do it. So if you are given something like 1/64, you know that this one is 2 raised to power 1/2 raised to power 1/2 raised to power 6. So it's 6 half lives. 6 half lives. So that is it. So we are going to use 5 half lives to solve this, since 1/32 is 1/2 raised to power 5. Right? So look at it. So we have first 5 life is just 50 days. Some students will even be doing it 50 days, 50 days, 50 days, 50 days, 100, 150, 200, 250 days. Or you just say 5 half lives of 50 days is equal to 5 times 50, 250 days. This is it. Very simple. So if you are given any question on half life, just get the half value of the number. Then that is the number of half lives times number of days. If it has to do with mass, divided by the number of mass, or you can easily apply it. So this is not a difficult thing at all. If we had time, I would have given you another question, but I will do that in our 40 complete questions and answers. 40 complete questions and answers in physics. All right. Get ready for that. All right. Let me continue. So please, I started to bring a question on work, energy, and power. Work done, work done, work done, work done. A boy drags a bag of rice, 50 kg, along a smooth horizontal floor with a force of 2 Newton applied at an angle of 60 degrees. This one is just like 20 kg, so it's not a full bag of rice anyway. But this force is not even enough to drag a bag of rice of 50 kg. Alright, 60 degrees to the floor. The work done after a distance of 3 meters is what? Work done. Alright, so let's look at this. Let's look at this. Okay, you can solve it. Start solving it. So now look at what we are going to do. We are going to have a diagram of it. This is the bag of rice. The force applied is 2 Newton, and this is the angle. This is 60 degrees. This is the distance covered. How many? 3 meters here to the horizontal. Listen, anytime you hear to the horizontal, please don't forget to the horizontal. Use what? Cos of the angle. But if you have vertical, use what? Sine. To the horizontal, cos. Vertical, sine. Vertical or down the plane. Use sine of the angle. Please, we are still going to do something about resolution of forces. Horizontal component, force, and vertical component of force. So, by the grace of God, just that we don't have time. Alright, so we are going to use cosine of this angle. So, work done is what? mgh cos theta. Formula. Force times distance times the angle involved. Alright, so what is the mass? This mg is already here, 2 Newton. If it is, sometimes you may be given as mass, kg, then you be given an acceleration due to gravity 10 or 9.8 approximate. 9.8 and approximate 10. So this one is the force, 2 Newton. 2 times, this h is standing as distance. That is why sometimes it's written as fs cos theta, like this. Force times distance cos theta, like this. Alright, so cos what? mgh, no, the distance, mg is 2 times distance 3 times cos 60. 2 times 3, 6. Cos 60, you don't need calculator. Look at it. I've always told students. So in UTME, most of the angles you'll be given are all these 60, 30, and 45. So let me tell you how to do it without calculator. Let me derive it very gently. Look at it, very simple. If you have something like this, we don't have time. 2, 2, 2. This is 60, equilateral triangle, 60. Then if we divide this thing by 2, this one will give you 30, 30. Then You have divided it 1, 1. So we can find here. So if we have, let's find here using this now. Here is 2, here is 1, here is x. Pythagoras. So x square equal to 2 square minus 1 square. So x square equal to 2 square. 4 minus 1, 3. So x is equal to what? Root 3. So you can always write it like this. You can always write it like this. 30, 60, root 3, 2, 1. So if you want to find cos 60, adjacent over hypotenuse, sine 30, opposite over hypotenuse, cos 30, adjacent over hypotenuse, tan 60, opposite over adjacent. Anything you want to get, you can get it within this place. Now 45, very quickly, without taking much of our time. Tan 45 is 1, 1. This is 45, so this place is definitely 45. Root 2. 1 square plus 1 square is 2. You know, square root of 2 is this. So if it's 45, this is 1, 1 root 2. Just know this. So we can finish this here. We can finish this here. Don't mind these things. Let me clean this so that we can continue. So cos 60, 60, where is our 60? 60, adjacent over hypotenuse, 1 over what? 2. That is SOHCAHTOA. Adjacent over hypotenuse, 2 divide 1, 2 divide 6, 3. The answer is 3 joules. Well done, 3 joules. Yeah, also A. We are getting A today, which means you are going to be an A student. Let's look at our final question today. Okay, one of you requested for this topic to be taught. So, density and relative density. So, I'm fulfilling my promise. An empty density bottle weighs 2 Newton. If it weighs 5 Newton when filled with water and 4 Newton when filled with olive oil, the relative density of olive oil is what? What is relative density? Most of the time, relative, anytime here, relative density, it is always compared to the what? Density of water. Density, relative density. Relative density. That of water will always be down here. This one is air over what? Water. Weight in air. Loss in weight in air. Weight in air over loss in weight in water. Weight in air over loss in weight in water. So relative density, air over water, or that liquid. Density in liquid and that of what? Water. Difference in liquid to water. Water is always down like this. So don't forget, it's not a difficult topic. Alright, so let's look at it. So it weighs 2 Newton normal weight. When it's now filled with water, it is 5. When filled with olive oil, it is 4. So they decided to give us 5 first before this one. Some of you get confused and put this one on. So this is that liquid over that of what? Water. So relative density is loss in this. Where is it? So we do loss in weight form of, right? Which is, this is for olive oil. So 4 minus 2. Archimedes principle. Archimedes principle. Loss in weight. When you put a bucket of water in a well, inside the well it is lighter. When it is still inside, down the water in the well, you check it, it is lighter. But once you bring it out, it becomes heavier. So weight in air is always more than weight in what? Weight in water. Inside the water there is upthrust force. Upthrust that makes it to like push it up. That is why ships sail on the seas. If there's enough upthrust force, a river can make a ship rather can float on a river. But the upthrust force in the river is not enough. That is why it cannot. So they have to dredge it. That is it. So there must be enough upthrust force for it to what? Float. There's also law of flotation. Go and study it. Archimedes principle and the law of flotation. But that's not what we are doing now because there's no time. You are preparing for UTME JAM. During the time for wire class, I will have enough time to explain all these. So keep following Mr. Primus. Let's go. So liquid 4 minus 2, loss in weight. Or then just relative density rather. So density of liquid over density of what? Water. Where is it? Difference in density. Alright, where is it? 5 minus 2. Alright, let's go. Density of this to the relative density of this. Alright, let's go. What is it? Weight of this to weight of this. 4 minus 2 is what? 2. 5 minus 2 is what? 3. Very simple. Finish it like this 2/3. So please keep following Primus Day. Keep following Mr. Primus. You are blessed. I will keep praying for you. For having subscribed and having joined us, you shall score high. So your assignment, what is obtruse first? What define relative density? Full definition in 3 ways. In 3 ways. In 3 ways. Then what else? What else? Archimedes principle and laws of flotation. Go and read all this. God bless you. Please keep sharing Mr. Primus lesson videos. Please keep sharing it. Thank you very much.